Hi, my name is Michael Pendezis, and welcome to online lesson number 7 in Probability and Statistics Math 241. Let's go what we did last time. So last lesson we talked about the normal distribution. We talked about the standard normal distribution also. And then 6.1 we talked about the mathematical expectation of a random variable, and that was capital E of X. Okay, and now in this next lesson, we're going to finish 6.1, and we're going to talk about 6.2, which is applications of E of X, and in 6.3, we're going to talk about the mathematical expectation of a function of a random variable. Okay, so let's get started. Okay, so let's finish 6.1, okay? So at the end of last class, we talked about the strong law of large numbers. And so let's talk about now example 6.7. And so we're going to suppose capital X is the length of life in years. Years of a certain battery. I'll just say a battery. Then little f of x is equal to 3/4 times 2x minus x squared, and that's for 0 less than x less than 2, and it's going to be 0 elsewhere. Okay, so for part A, we're going to show that E of X is equal to 1. Okay, using the definition of E of X. And so E of X is equal to the integral from negative infinity to infinity of x times f of x dx. And that's by the definition of the expectation of a continuous random variable. Remember, this is for a continuous random variable. Okay? And since x is the length of life in years, so we're talking about time, and so when x is the amount of time a battery lasts in years, we're talking about values of x which make up a non-discrete set. And so it's a continuous random variable, but and it's also the set is of a continuous type, so it's a continuous random variable. Okay, so let's calculate this. And so now from 0 to 2, we can get a non-zero value of the integrand because f of x is non-zero. And so that's going to be non-zero only between the values from 0 to 2. So we only have to calculate the integral from 0 to 2. And x is itself, and then f of x is 3/4 times 2x minus x squared. So that's f of x. So x times f of x dx. And so if you calculate the integral from 0 to 2 of x times that, by the fundamental theorem of calculus, you calculate the integral and you get 1. And so we showed that E of x is equal to 1. Okay. And part B, I'll just say if we bought 2,000 batteries, we expect that the average length of life for that battery to be 1 year. And that's by the law of the strong law of large numbers. And the strong law of large numbers again said that the probability of the limit as n approaches infinity of x1 plus x2 plus dot 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 plus xn over n equaling to mu is equal to 1. And what that means in words is that essentially, since you can't repeat an experiment an infinite number of times, if you repeat an experiment a large enough number of times and record the value of your variable for each of those n times, you take the average of those n values by adding them up and dividing them by n. The average of a very large number of results of your average of the very large number of x's should be about the expected value of your experiment. And so since we found e of x, the expected value is 1, we should expect that if the x of i's are the life or how long each battery lasts, and we take the average of how long each of those 2,000 batteries lasts, since we did a large number of experiments, n, 2,000, then that average should be very close to 1. Remember, mu is e of x. Mu is used to equal e of x, and so since e of x is 1, it's saying that for a very large number of batteries, the average lifetime of a very large number of batteries will be close, if not equal, to the expected value of 1. Okay, that's where the 1 comes in from there. Okay. Okay, and so that's the end of 6.1. Okay, and so the homework for this section is on pages 182 to 183, and it's numbers 1, 3, and 9. Okay, and so that's the end of 6.1. Okay, and now so for 6.2, applications. Okay, so 6.2 is applications. And so 6.2.1 is on fair games. Okay, so definition of a fair game. A fair game is one in which the expected net gain of each player is 0. Okay, so that's a fair game, right? So it's a type of game you'll never see at a casino, right? So this is a game where you should expect that if you play the game enough times, a large number of times, you should expect to end up even. Okay, that's a fair game. Okay, so that's the definition of a fair game. And so let's look at example 6.8. And in 6.8, we're going to decide whether or not this game I'm going to define is a fair game, whether or not it's a fair game. Okay, so the game is called Chuck-a-Luck. So that's the name of the game, Chuck-a-Luck. And so the player pays $1. Okay, so the player pays $1, and he chooses a number from 1 to 6. Okay, so the player pays $1 and he chooses a number from 1 to 6. Okay, 3 dice are rolled. Okay, 3 dice are rolled, and if the number chosen appears 1, 2, or 3 times, the player receives $2, $3, or $4 respectively. And the question is this a fair game? And another question is, if not, what should the fee be? So it is okay, so we have 2 questions here. Okay. This question, and then afterwards this question, in that order. First this question, this question. Okay, so again, the game is called Chuck-a-Luck. Player pays $1, chooses a number from 1 to 6. 3 dice are rolled. The number chosen from 1 to 6 in 3 dice rolls, if it appears once, he receives $2. If it appears twice, he receives $3. And if it appears 3 times, he receives $4. It could also appear 0 times, in which case he doesn't receive any money. Okay? And so that's not all the ways it can appear. It's just those are the numbers where you make money, some amount, right? But don't forget, he pays $1, right? So even though he makes this amount for those rolls, he paid $1 in order to play the game. And so he's not making a net $2 here. He's making a $1 net here. He's making a net $2 here, and he's making a net $3 there, right? If the number he chose, 1 to 6, appears once, he gets $2 after paying $1, and so he makes a net $1. And the same applies to the other 2, right? Okay, so so the solution I'm going to put over here. Okay, trying to give myself a little bit of room. So the solution to example 6.8 we're going to put on this side. And so I'm going to let x equal the net gain of the player in units of $1. Okay, so if x is 2, then he made $2, right? If x is -1, he lost $1. The units are $1. Okay, what's that mean? Okay, and so to find the probability, so to find f of x, which is the probability that capital X equals some fixed value little x, we consider this game, we consider each roll a Bernoulli trial. And so once you hear that I'm considering each roll a Bernoulli trial, you're now scared, right? Okay, so now each roll is called a Bernoulli trial, right? That means that each roll is either a success or failure. Okay, so each time you roll the dice, it's either a success or failure. Now that success or failure is determined by what number you chose. Okay? Okay? Right, so when you choose one of the 6 numbers, its success is only if you get that one number. So the probability of success in any given Bernoulli trial is 1/6, right? There's a 1/6 chance that the number you chose from 1 to 6 is the number you get when you roll a die. And the probability of failure is 1 minus that probability, right? But then just thinking of what's happening in the experiment, if you choose a number from 1 to 6, the probability of failing to get that number on a roll of dice is rolling any of the other 5 numbers out of the total 6. So probability of failure is 5/6. Okay? And so, okay, so but that's the probability of just success and failure. Now the probability that x is equal to -1. So x is the net gain of the player in units of $1. And so how could x be -1? Well, if you choose one of those numbers and it appears 0 times, if you never get the number, you don't make anything. So you pay $1 for a number, you pay $1, you choose a number, you roll the dice 3 times, and it appears 0 times. That means you don't get anything. So all that happened was you paid $1 to get nothing. And so that's how your net gain is -$1. So probably x is equal to -1 is the probability that you choose a number of 1 to 6, you roll 3 dice, and it appears 0 times. And so what that is it's the binomial probability 0, 3, 1/6. And reminding you what that means. In your experiment, you have 3 Bernoulli trials in your experiment. You roll the dice 3 times. So that 3 means you roll the dice 3 times. The 1/6 is the probability of success. Okay? So each roll of a dice is a Bernoulli trial because each roll of a dice is either success or failure to get the same number you chose. So each roll of a dice is a Bernoulli trial. You roll 3 dice, so there's 3 Bernoulli trials. The probability of getting the number you chose is 1/6 in each trial. And this is the probability that x is -1, the probability that your net gain is -$1 is a probability that your number appears 0 times. So that means that you succeed 0 times at rolling the correct same number you chose. So this is the binomial probability that you have 0 successes in 3 Bernoulli trials with the probability of success in each trial is 1/6. And so the value of that is equal to 125 over 216. And so that's computing the binomial probability, right? And actually, so maybe to remind you of that, right over here, b of 0, 3, 1/6 is equal to 3 choose 0, 1/6 the 0 power, 5/6 cubed. And that's equal to 125 over 216. Okay. The probability that x is now equal to 1, well, that's if your number appears once, right? Okay, so you pay $1, you choose a number from 1 to 6, you roll 3 dice, the number you chose appears once. That means they give you $2 after you paid $1. So your net gain is $1. But that happened because your number appeared once. So you chose a number from 1 to 6 and it appeared once in the 3 dice roll. So that means that you succeeded once out of your 3 Bernoulli trials of getting the number you chose. There's still 3 Bernoulli trials, and there's a 1/6 probability of success. And so the binomial probability of 1, semicolon 3, 1/6, of 1 success in 3 Bernoulli trials with a probability of success is 1/6. That's equal to 3 choose 1, 1/6 to the first, 5/6 squared. That means that 1 out of your 3 Bernoulli trials is success. The probability of success was you succeeded once and you failed twice, right? 1 success out of 3 trials means 1 success and 2 failures. And you multiply all that out and you get 75 over 216. Okay, so this is 75 over 216. Okay, and then the probability that x is equal to 2. Well, then that means that you paid $1, you chose a number from 1 to 6, you rolled 3 dice. The number you chose from 1 to 6 appears twice, and they give you $3. So you paid $1, you made $3, your net gain is 2. So your net in units of dollars is 2. So probably x equals 2 is probably your number appears twice. That means that you have 2 successes in 3 Bernoulli trials where the probability of success is 1/6. And so now the value of b into semicolon 3, 1/6 is equal to 3 choose 2 times 1/6 squared times 5/6 to the first. And so then that's equal to 15 over 216. Oh, I boxed it there. Okay. So this is 15 over 216. Okay? Now the probability that x is equal to 3, the probability that your net gain is 3 is you pay $1, you choose a number from 1 to 6, you roll 3 dice, your number appears all 3 times. So you chose a number, you roll 3 dice, it appears in all 3 of them. You make $4 for that. You should make more. You say you make $4, you paid $1, you make a net of $3. And so that's rare. And so 3 successes in 3 Bernoulli trials where the probability of success in each trial is 1/6. And so to calculate that, that's just the binomial probability of 3 successes in 3 trials where the probability of success is 1/6. That's 3 choose 3 times 1/6 cubed times 5/6 to the 0, and that's equal to 1 over 260. Okay, and so what I'm boxing here is the probabilities of each value of your discrete random variable. Right? X is the net gain of a player in units of $1. There's only 4 possible values of x, -1, 1, 2, and 3. And so we found the probability of each possible value of our discrete random variable x here. And so remember, the question is this a fair game? A fair game is one in which we expect the net gain of each player is $0. And so what that means is the expected value is 0 for a fair game. So the question is the expected value of this experiment equal to 0? Okay? So fair game is when doing the expected net gain, that's the expected value of each player is 0. Okay? So the question is the expected value 0? And so now here we're going to compute E of x. And so from that, we're going to compute E of x, and it's going to equal the sum over all possible values of x times f of x by the definition of the expected value of a discrete random variable. Discrete, right? -1, 1, 2. Okay. So now for each value, -1 times f of -1 plus 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3. And so each probability, these are the probabilities, and you just multiply them by those numbers. And so this is -1 times 125 over 216 plus 1 times the probability x is 1, which is 75 over 216, plus 2 times the probability x is 2, which is 15 over 216, plus 3 times the probability x is 3, which is 1 over 216. Okay, and so now you just, you calculate that, and you get, this is equal to -17 over 216. Good, and so then this is equal to -0.0787. So the expected value of our discrete random variable is -0.0787. So this is not a fair game. Right? This is not a fair game, and that's because E of x does not equal 0. So E of x does not equal 0 equals -0.0787. And so that means that we do not expect the net gain of each player to be 0. It's not a fair game. Okay, and so we answered that question about whether or not it's a fair game, whether or not the expected value of our discrete random variable is 0. It's not. Okay, so that's the first question. And so, okay, so I'm going to erase where I'd say what the game is, because now we have all this information. The second question is, what is the value, what should the fee be so that it is a fair game. Okay, and so I'm going to let K denote the fee. So the second question is, what should the value of K be? What should the fee be so it is a fair game? Well, the expected value of our discrete random variable is that if you pay if you make $0 and you pay K dollars, the probability is 125 over 216. That's the probability that you rolled 0 of the numbers you chose. 0 many of them, right? And so you make $0, but you pay K dollars for that to happen. Well, you could also make $2 if it shows up once, and the probability of it showing up once was 75 over 216. You could also make $3 and pay K dollars if the number appeared twice, which is 15 out of 216. And then plus, you could make $4 and pay K dollars if it appears all 3 times, and the probability of that is 1 over 216. Okay? So if your number appears 0 times, you make $0 and you paid K. That's the probability. The probability of your number appearing once is this. If it appears once, you make $2 and you pay K dollars. If the number you chose appears twice, that's the probability. You make $3, you pay K dollars. If the number you chose appears all 3 times, that's that probability. You make $4 and you pay K dollars. And so this is the amount you'll make. So this is the expected value of your discrete random variable. Okay? And so what we're saying is that we want to find the value of K that makes E of x 0. Find K that makes E of x equal to 0. Find the value of K that makes this a fair game, makes E of x equal to 0. And so what we want is E of x to equal 0 here. And so for what value K do you plug in here so that the expected value is 0? And so you just you just solve for K in this equation, 0 equaling to that. And what you find is that K is equal to 199 over 216. And that's approximately 0.92. Okay, so K is approximately 0.92. Okay, so now we showed that this is not a fair game, and we found the fee so that we can make it a fair game. Instead of paying $1, pay 92 cents. Okay? And the meaning of this expected value is that if you play the game a lot of times, you should expect eventually that on average you lost 8 cents, about 8 cents, 0.08 of a dollar. Okay? Okay. Okay, so 6.2.2, and that's on decision problems. Okay, and so here is example, here's example 6.9. A company sends a number of employees to an annual conference. Held in a hotel. And so the hotel, it costs $30 per day per person. Okay, so that's how much the hotel costs. Okay, so hotel costs $30 per day per person. And that's if reservation received uh, 30 more days in advance. Okay? There's a $15 cancellation fee. Per person. Okay, and the regular rates is $40 per day per person. And that's the regular rate if you don't make a reservation 30 or more days in advance. That's the regular rate. Okay, so management doesn't know the exact number of people they'll need to make reservations for. They don't know the exact number of people who will go. Okay, and so what management has concluded is that they think first that X is the number it will send. So X is the number of employees that will go. Okay, and that X is a random variable with probability function. F of X is equal to 1/4, and that's for X equals 4, 5, 6, or 7. Okay, so the company will send either 4, 5, 6, or 7 people, and the probability of any of those numbers is 1/4. Okay, and so the company feels confident about that. Okay, that it will send either 4, 5, 6, or 7 people, and the likelihood of each amount is 1/4. Okay? And so the question is, should the company make advance reservations? Okay? And if so, how many? And by how many, and if so, how many? I mean the amount that will minimize the cost in the long run. Okay? And so that's the question. So I'm boxing the question and circling the information the problem needs to know. Okay? And so that's the question. Okay? Written in a way so that it's easier to read. Okay, so we want to find, should the company make advance reservations? If so, how many? Okay. So we're going to here's the solution. We're going to let y sub I equal the cost in dollars if the company makes I reservations. Okay? So y sub I is the cost of dollars if the company makes I reservations. Okay? So, so I'm going to put, we'll make a little table here. And so here is going to be y sub I. And so the cost of dollars the company makes I reservations. Well, they'll either send 4, 5, 6, or 7 people. So we want to talk about y sub 4, y sub 5, y sub 6, and y sub 7. Okay, so we either want to know the cost of dollars if the company makes 4 reservations, 5, 6, or 7. Since it saves money on reservations, making reservations, since what they think is that there's not going to be any other number, then they should make at least 4 reservations, no matter what, because there's going to be at least 4 people. Okay, so there's no reason to make 8 reservations when they know there won't be more than 7 people going. Okay. So we want to know the cost for the company if it makes 4, 5, 6, or 7 reservations. Well, how many people are attending? Either 4, 5, 6, or 7. And so here, we're going to have the values of X. Actually, I'm going to pull this Y sub line. So here in this table, I'm going to say X is equal to 4. Here I'm going to say X is equal to 5. Here X is equal to 6. And here X is equal to 7. Okay, so either the company makes 4, 5, 6, or 7 reservations, and either 4, 5, 6, or 7 people go. Okay, and so what are the values of Y sub 4? But these are the values of Y sub 4. Okay. So in the boxes are the values of Y4, Y sub 4, Y sub 5, Y sub 6, and Y sub 7 for these X. Okay. Okay. So if they make reservations for 4 people, then they're paying $120 for those 4 reservations. Right? And all 4 of them attend. And so they paid, it cost them $120. It's cost of dollars. So it costs them $120 to make 4 reservations and 4 people go. 4 times 30. I mean, yeah, 4 times 30. Okay, good. Now, if they make 4 reservations, they pay $120 for those 4 reservations, and 5 people go, and 4 of them they pay this fee for. But 5 people go, so 1 person pays the regular fee, so it's 120 plus 40, and they have to pay 160 for the additional person they didn't make a reservation for. 6 people go, they pay 4 in advance, $30 each reservation, it's 120. Then they have to pay 2 more at the regular rate, so it's 120 plus 80, that's 200. Right? And now 7 people go, they make 4 reservations, they pay 30 each, they pay $120 for the first 4, and then the 3 remaining have to pay the regular rate of 120. So they pay 120 in reservations and another 120 in regular fees, so they have to pay $240 if 7 people attend. Okay, now if 4 people attend here, they make reservations for 5 people. And so they pay $150 for reservations, but only 4 people go. Okay, so actually, there's a $15 cancellation fee. So that 5th person who didn't go, they can get the $30 back, but they pay a $15 cancellation fee. So they only pay $15 for that 5th person who doesn't go. So that's $135. Okay. So if they make 5 reservations, 4 of them go, so that's $120, 4 times 30. They pay $120 for making reservations for 4 people to go. The 5th person doesn't use it, and so they pay $30, but there's a $15 cancellation fee. They cancel the $30, and they pay $15 additional dollars, so it's $120 plus 15, $135. If 5 people go and they make 5 reservations, they use all 5 reservations, and they pay $150. Okay? If 6 people go and they made 5 reservations, then the 5 reservations are used at $150. Then the 6th one, they cancel it and they pay $15 for that. And so now it's $175. Oh, no, sorry, no, sorry. 6 people attend, then 5 reservations, $150, and then they pay another $40 for the additional person, $190. And then if 7 people attend, 5 reservations, 5 times 30, they pay $150 in reservations. 2 more have to pay the regular fee. It's 150 plus 80, that's 230. Okay? If 6 people, reservations for 6, 4 of them are used, that's 120 plus 2 cancellation fees. 120 plus 30 is 140. Now, 6 reservations, 5 go, 5 are used, that's 150 plus a $15 cancellation fee, that's 165. 6 reservations, 6 people go, they use all 6 reservations, 6 times 30 is 180. 6 reservations, 7 people go, 6 reservations are used, that's 180 plus 1 additional regular fee, that's 220. Now, 7 reservations are made and 4 people go. That means 4 reservations are used, that's 120. 3 cancellation fees, that's 45 plus 120, that's 165. Now, if 7 reservations are made and 5 people go, 5 reservations are used at 150, then 2 are canceled, that's 30, so 150 plus 30 is 180. And then 7 reservations made, 6 people go, 6 reservations are used at $30 for each person per day, and so it's 180. 180 plus 1 cancellation fee is 195. And then here, 7 reservations made, 7 people go, so all 7 reservations are used, and that's $210. Okay, and so that's our table. Okay, so E of y sub 4, okay, well, by the definition of expected value, it's the sum over the possible values of y sub 4 of x times f of x. These are the possible values of y sub 4, 120, 160, 200, and 240. Okay, and so each of these values of y sub 4, which is I'm saying is x, multiplied by its probability. The probability of each is 1/4, and so this is equal to each possible value of y sub 4 multiplied each respectively by 1/4. So 120 times 1/4, probably that 4 people go, x is 4, plus 160 times the probability that 5 people go, which is 1/4, plus 200 times the probability 6 people go, which is 1/4, plus 240 times the probability 7 people go, which is 1/4. And you add up those products, and what you get is E of y sub 4 is equal to 180. So that's 180, E of y sub 4. E of y sub 5 is equal to each value of y sub 5 multiplied by the probability of that many people attending, which is 1/4, and adding up the product. So it's 135 times 1/4 plus 150 times 1/4 plus 190 times 1/4 plus 230 times 1/4. So you add up, you calculate each product, and you add them up, and you get E of y sub 5 is equal to 176.25. So that's 176.25. Okay, and then E of y sub 6 is equal to each value of y sub 6 multiplied by the probability of that many people attending, which is each 1/4. So it's 150 times 1/4 plus 165 times 1/4 plus 180 times 1/4 plus 220 times 1/4. And so you add up those, you calculate each product and you add them up and you get 178.75. And then finally, E of y sub 7 is equal to each value of y sub 7 multiplied by the probability of that many people attending, still each one is 1/4. So it's 165 times 1/4 plus 180 times 1/4 plus 195 times 1/4 plus 210 times 1/4. And so you add up those products and you get E of y sub 7 is 187.5. Okay? Okay, and so these are each of the values. These are the values of each one. And so the amount the company would have to spend on average, you know, averaging out all the possible number of people who would attend, this is the smallest one. 176.25 is smaller than 180, 178.5, and 187.5. So since this is the smallest value, you get that from y sub 5. Y sub 5, which is making 5 reservations. And so the company should make 5 reservations because the expected value of y sub 5, which is 176.25, is smaller than the expected value of any of the other discrete random variables of finding the amount the company spends, whether it makes 4, 5, 6, or 7 reservations in advance. Making 5 reservations in advance in the long run will, on average, cost the company the least amount of money. Okay? So should the company make a advance reservation? Yes, because it'll save money. And if so, how many? It should make 5 reservations. That's the one that results in the smallest expected value. So the answer is yes, it should make advanced reservations, and it should make 5 reservations. Okay, it should make 5 reservations. Right, and you can see it should make reservations because if 4 to 7 people are going, then you might as well make 4 because you'll save money on all 4 of those reservations. You'll save $10 in each reservation, right? Because when 4 people go, you pay 40. With the reservation, you only pay 30. So right off the bat, it's obvious that the company should make advanced reservations. Okay. So next example. An inventory problem. Okay. So in any one week, I'm going to call X the number of requests for a magazine. So that's basically the number of requests for a magazine is how many you could sell, right? So if 1,000 magazines are requested and you only have 100, you would sell 100, you could have sold more, right? So that's just how many you could sell, the number of requests, okay? And this is a random variable. And its probability function, little f of x, is equal to 5/12, and that's for x equals 3. It's 4/12 for x equals 4, 2/12 for x equals 5, and 1/12 for x equals 6. Okay, so here it's not 1,000 requests. You have 3, 4, 5, or 6 requests for your magazine. Okay, and those are the probabilities of having those many requests, and it adds up to 1, and so that's good. There'd be a problem if it didn't. Okay, so the magazine, we're talking about a magazine here the whole time, okay? So it sells for $1 each, okay? So the magazine sells for $1, and the cost to the owner for each magazine is 50 cents, half a dollar. So each magazine costs the owner 50 cents, and when the owner sells a magazine, he makes $1. And so the question is, how many magazines, mags is short for magazines, how many mags should he order per week? to max expected profit. Okay, so how many magazines should the store owner, the person, order to maximize expected profit? That's the question. So this is what we need to know, and that's the question the problem we want to solve. Okay, so let's do that over here. Okay, so a solution. I'm going to let y sub I equal the profit in dollars. That's in dollars. If the owner buys I magazines. Buy I magazines. Okay, and so I'm going to make a table. So this table is going to have okay, so x, we'll put x here, y sub 3 here, y sub 4 here, y sub 5 here, y sub 6 here, and the probability that x is equal to some fixed value little x there. Okay, and so either x is going to be x is either going to be 3, 4, 5, or 6. Okay. And so, okay, so these are, okay, so X is the number of requests. Okay, so if the owner buys 3 magazines and 3 are requested, then if he buys 3 magazines, it costs the owners 3.50 cents, 3 times 50 cents. It costs him $1.50 to buy 3 magazines. But then he sells all 3, so he makes $3 and it costs him $1.50, and so the owner makes $1.50. If he buys 3 magazines and he sells all 3 of them, he buys 3 magazines for $1.50, he makes $3 from selling the 3, net $1.50. If he buys 3 magazines and 4 are requested, he buys 3 magazines for $1.50, but he only can sell 3 of them because he only bought 3, and so he still makes $1.50. Okay? If he buys 3 magazines, which costs him $1.50, and 5 are requested, he can only sell 3 of 3 because he only bought 3, and he still makes $1.50. And the same thing applies for 6. If he buys 3 magazines, 6 are requested, he can only sell all 3 of the magazines he bought, and he only make $1.50. If he buys 4 magazines, but 3 are requested, he buys 4 magazines, 50 cents each. It costs him $2 to buy 4 magazines, for him to get 4 magazines. He only sells 3, so he makes $3, and it costs him $2, and so he makes a net $1. So if it costs him $2 to make these 4 magazines, and now he makes $4 because he can sell 4 because 4 are requested, 4 minus 2 is $2. If it costs him $2 for 4 that he has, and 5 are requested, he can only sell all 4 of them, and he still only makes $2. And here he only makes $2, right? He gets 4 magazines, $2 cost. He can only sell all 4 of them. He can't sell 6, he only has 4. So he still makes $4 and it costs him $2. Okay, $2 net. If he pays for 5, it costs him $2.50 for those 5, but he can only sell 3 of them. So that's $2.50. He makes $3, so he only makes 50 cents here. Okay. Now if it costs him $2.50 and he can sell 4 of them, he can make $4 and he can make $1.50. If it costs him $2.50, he can make $5 and he can make $2.50. If it costs him $2.50, he can only sell 5 of the 6 and he still only makes $2.50. If he gets 6 magazines, it costs him $3. It costs him $3, he makes $3, he makes a net of 0. If it costs him $3 and he makes $4, he makes a total of $1. If it costs him $3 and he makes $5, then he makes $2. If it costs him $3 and he makes $6, he makes a net $3. Okay, and so this table is telling us for each value of X, the profit that the owner makes if he buys 3 magazines, if he buys 4 magazines, if he buys 5, and if he buys 6. And now the probability that X is 3 is 5/12. The probability that X is 4 is 4/12. The probability that X is 5 is 2/12. And the probability X is 6 is 1/12. And this adds up 3, 7, 12. Adds up to 1. Okay? Okay, so now if you wanted to find the expected value of y sub 3 is a discrete random variable. Its only possible value is 1.5. Y sub I is the profit if the owner buys I magazines, and the only amount of profit we see that he can make if he buys 2 magazines is $1.50. And so this is the sum over the possible values of y sub 3 of those values times the probability of getting those values. And so that's $1.50 times the probability that times the probability that y sub 3 is equal to 1.5. And so, okay, so this is not the same x, and so I want to keep the notation the same. This x is not the same. This x is the number of requests, and this x, I'm going to call this y, but I don't want to confuse you. This is the sum over the values of y sub 3, the value of y sub 3 times the probability that y sub 3 values. So this is, in this case, there's only one value of y sub 3, so it's that value of y sub 3, 1.5, times the probability that it gets 1.5. Well, it's always 1.5, so the probability is 1. So this is 1.50 times 1, which is 1.50. So the expected value of buying 3 magazines is $1.50. The expected value of y sub 4, the expected value of the profit if the owner buys 4 magazines, well, it's the sum over the values of y sub 4, each value times its probability. And so now the possible values are $1 and $2. And so it's $1 times the probability that y sub 4 equals $1 plus $2 times the probability that y sub 4 is equal to $2. Well, that's 1 times the probability of y sub 4 is 1. That's 5/12. Plus 2 times the probability of y sub 4 is 2. That's this probability plus this one plus this one. That's 4, 6, 7/12. And so that's 5/12 plus 14/12. That's 19/12. And 19/12 as a decimal is 1.58. So you just add up, you go 1.58. Okay? Now E of y sub 5 is equal to the sum over the possible values of y sub 5 of those values times the probability of getting those values. And so the possible values for y sub 5 are 50 cents, $1.50, $2.50, and $2.50. So you get these 3 values. And so it's 50 cents times the probability that y sub 5 equals 0.5, 50 cents, plus 150 times the probability of y sub 5 equaling 1.5, plus 2.5 times the probability that y sub 5 is equal to 2.5. Okay, and so the probability that y sub 5 is 0.5 is 5/12. Plus 1.5 times the probability y sub 5 is 1.5, which is 4/12. Plus 2.5 times the probability y sub 5 is 2.5, which is 2/12 plus 1/12 is 3/12. And if you add those, if you multiply that out and add it up, you get 1.33. Okay, so that's e of y sub 5. I'm going to do e of y sub 6 over here. E of y sub 6, the possible values of y sub 6 are 0, 1, 2, and 3. And so for each one, 0 times the probability of y sub 6 equals 0, plus 1 times the probability of y sub 6 is equal to 1, plus 2 times the probability of y sub 6 is equal to 2, plus 3 times the probability of y sub 6 is equal to 3. Right? Taking each value of y and multiplying it by the probability of getting it. Probability of getting y sub 6 equal to 0 is that. Probability of y sub 6 is 1 is that. And you plug those in, and then you multiply and you add, and you get this is equal to 0.92. Okay? Okay, and so we see that the smallest amount is e of y sub 6. And so the question is, how many magazines should he order to max expected profit? Well, the expected, this y sub I is the profit. And so the expected profit here is lower, always lower. So we want profit, how many? To max expected profit. So then if you want max expected profit, that's e of y sub 4. E of y sub 4 gives the largest expected profit. And so that means that the magazine owners should buy 4 magazines. How many magazines? You should buy 4 magazines to max the expected profit. Okay. The answer is 4. Let me answer the question. Okay, so that's that one. Okay, and so now let's go to the next topic, which is 6.2.3, and that's a Monte Carlo methods. Okay, so example 6.11 is Monte Carlo method for calculating a definite integral. And so this is kind of cool. You can use probability to find a definite integral, the area under a curve. Okay? So let's assume, so our assumption is going to be that phi of u is continuous on the interval a less than or equal to u less than or equal to b. And the function is bounded below and above by 0 less equal to phi of u less than or equal to capital A. Okay? That means the smallest the value of the function could be in this range of u values is 0, and the largest value it could be is capital N. Okay? So that's our assumption. Now the experiment is the following. So let me separate the assumption here with this circle. That's what we're assuming. And then the experiment is a random point u comma v is selected such that a is less or equal to u less or equal to b. And so u is somewhere in these range of u values, and the v is at least 0 and at most capital N. And we're going to let x be the random variable, let capital X be a random variable defined as capital X is equal to 1 if u comma v, this point, is below the curve of v of u, and 0 otherwise, if it's not below it. 0 if that happens, 0. 1 if that happens, 0 otherwise. Okay, that's our random variable capital X. Okay, so we're assuming this, and this is our experiment. Okay, so that's our experiment here. We're going to observe that the probability that X is equal to 1, right? The probability that the point u comma v we select at random here is below our curve. That's just equal to, well, the area under the curve divided by the area of the rectangle. And so what do I mean by that? If you have this graph here, where these are the values of u, this is A, this is u equals A, this is u equals B. A is only between A and B inclusive. Capital M is our upper bound, 0 is our lower bound. Right. So our u comma v here, selected at random, it has to, the first coordinate of this point has to be in this range of values, and the v here is at least 0 and at most m. So the u comma v we select is somewhere in this box. This u comma v is somewhere in this box. Okay, it can be on the boundary also. Now, if you have a curve phi of u defined on here that's bounded below by 0 and above by capital M, and it's continuous, you can draw this curve without lifting your hand. So for instance, let's say this was the curve. Okay, so let's say that was the curve, but now we're only considering from A to B. So we're only thinking of what's happening with this continuous function inside this box. Right? Okay, that part. We're not worried at all about this part or that part. Now, the value, if you think of choosing a point u comma v in this box as shooting an arrow, and where the arrow hits in this box as being the point you select. Well, if you shoot an arrow in this box, the probability that X is equal to 1, that's the probability that the point you hit is somewhere in the shaded region below the curve. Right? So what's the probability you hit the shaded region in this box? So assuming you only hit in the box, you don't hit the arrow outside the box. Assuming you hit inside the box, the point is inside the box, what's the probability it's in the shaded area? It's just the area under the curve. It's the area of the shaded region divided by the total area of this rectangle. And so what that is equal to is a definite integral from A to B of phi of u du. This definite integral is the area under the curve, right? The area underneath the curve from A to B, a continuous function, is the definite integral from A to B of the value of the function as the integrand. Right? This definite integral is just the area of the shaded region. Then you're dividing it by the area of the rectangle, which is just base times height, b minus a times capital M, or capital M times b minus a. And so this fraction, this differential over capital M times b minus a, is the probability that your point is in the shaded region, or the probability that X is equal to 1. Right? That your point that you hit is below the curve, not above it. Or on. Okay. Probability though of hitting the edge is 0. Okay. Now the probability that X is equal to 0 is 1 minus the probability of the complement, which is the probability X is equal to 1. There's only two possibilities, so if X is not equal to 0, it's equal to 1. So the complement of the event X equals 0 If x is not equal to 0, then the only option is that x is equal to 1. So that's 1 minus the probability of the complement event, x equals 1. And we found that there. And so you could say it's 1 minus that fraction, probably x equals 0. Okay, and in the book, this is figure 6.1. Okay? And so therefore, as a result of all this, this implies that E of x for this experiment is 1 times the probability x equals 1 plus 0 times the probability x equals 0. But regardless of what this is, it's 0 times it, and so that's 0. That's nothing, right? And so this is 1 times the probability x equals 1, which is this fraction, the differential from a to b of phi of u du over capital M times b minus a. So E of x is equal to that. Okay? So E of x, the expected value, is this. Okay? By the strong law of large numbers, we should see that the average value of repeating the experiment n times, if for n large enough, you would take that the sum of the values over n, the average values, would be approximately E of x with great probability. Right? So instead of it being the limit, saying the limit is 1, the limit of the probabilities is 1, the probability of the limit of this is 1, you could say that the probability is very close to 1, that this will be about E of x. So with great probability, you can say that the average of the values of a large number of experiments is approximately E of x. And so that implies that the definite integral from a to b of phi of u du is approximately m times b minus a times the sum Okay, so if you solve for this differential here, you would get, if you solve for this here, you would get E of x times capital M times v minus a, and E of x is approximately this. So what you're doing is you're substituting this guy for this, and you're saying the sum over n times m times v minus a is that. Okay? And that's with great probability. So with great probability, you could say that this differential is approximately capital M times v minus a times the average value of x. Right? So if you repeat this experiment a large number of times, n times, what would be the average number of times you hit the shaded region? Right? So let's say I shoot an arrow at this board 1,000,000 times. On average, how many times would I hit the shaded region, right? So if I shoot an arrow only in the box here 1,000,000 times, and I record how many of those times I hit the shaded region, I take that number divided by the number of shots I take 1,000,000, and I multiply it by capital M times v minus a. That should be an approximation for this area. Okay? Okay, and so that's example 6.1.1 right here on the board. Okay, the next example will take a little bit of time, and so I'm going to leave the next example for the next lesson before we finish this section. And so I will close this lesson now, and so look forward to you seeing my next online video. Have a good day.